Okay, so as I was saying, welcome everyone to another episode of our series of expert talks. Today we have the pleasure of being able to listen to Daniele Oriti. Daniele has a long history of contributions to the field, which makes an introduction particularly difficult. But I will do my best. As a quick synthesis, I have some notes here. So Daniele did his PhD at Cambridge with Bruce Williams. I forgot to write down the thesis, but if I remember correctly, it was called On Spin Foam Models of Quantum Spacetime. And then he did a postdoc, well, a number of postdocs, one in Cambridge, Utrecht, and also at the Perimeter Institute in Canada. He was then awarded Sofia Kovalevskaya grant to constitute the junior research group at the Albert Einstein Institute, and is currently a senior group leader at the Ludwig Maximilians Universität in Munich, as I say, with the Heisenberg grant, where he is sitting right now in his office. As I said, so Daniele has a long history in the field, full of contributions. He is probably most known for his proposal of the group field theory approach to fundamental cosmology. That's 20 years of work and dedication to the project of quantum gravity. As far as I understand, Daniele hasn't yet quantized gravity, but that's something that I think we can forgive him. We're very happy to listen to this talk on group field theory. You can ask questions during the talk if you want. There's also a form for anonymous questions in the chat. Daniele, please go ahead. Thank you very much.
Yeah, thank you for the introduction. I thought you only wanted an introduction, not to the formalism and not the solution to the problems. Otherwise, I would have prepared a different talk. So now it's too late, and indeed, I will just stick to the assignment. And I will give an introduction to the group field theory formalism for quantum gravity. And I stress that because the formalism, as I will try to emphasize, is a bit, is rather general, and it has in fact found a number of other applications, but I will not really mention them. So I will really start with the intuitive idea, and my hope is that once you got the intuitive idea, the rest is like just fleshing out a little bit some of the elements I'm going to introduce now at the intuitive level, and understanding a bit where things are going. But most of the job will have been done with the first few slides. So let's see if I managed. So, well. Can you see the whole slide? Because I'm partially covered by the Zoom.
I think we can, yes.
Okay, very good. And I remember what I wrote, so I don't need to read the titles. So, I mean, first point, just imagine chopping up space in building blocks. Now, this sounds a bit violent, but it's the usual thing that is done when you introduce a lattice discretization of a smooth manifold and of its associated geometry. So I'm talking here about so I have a 3D picture here. I will be referring to space-time in the next couple of minutes, but I use the 3D picture for easiness. So just like you can discretize the topological structures, you can discretize fields and dynamics on the same topological structures. And so for Einstein gravity, it would mean introducing the most obvious counterpart of the metric field on a smooth manifold, which is a set of elementary distances, the edge lengths, on a lattice that replaces the smooth manifold. And you can then write also a discrete counterpart of the Einstein-Hilbert action using this as fundamental variables, and that is the so-called Regge action. Now, so you've seen all that probably because, first of all, because the idea is, is one standard strategy to make sense of a continuum path integral for a field theory. And it also, of course, led to a number of quantum gravity formalisms. So this is, in fact, to go to this discrete framework is the basic idea behind the lattice quantum gravity, and that could take the form of quantum Regge calculus, so-called, in which you directly try to write down a path integral in which the edge lengths are on a given lattice are the fundamental metric variables. So you use the exponential of the Regge action as the measure, together with some additional contribution to the integration measure, and you perform the integrals. Of course, the full theory is to be recovered when you have an infinite number of degrees of freedom. So in particular, when you refine your lattice infinitely. So this is, the idea of Regge calculus and of lattice path integrals in the straightforward fashion. Now, in the case of gravity, there is also a complementary strategy that you may have also heard about. The geometry of a discrete lattice is encoded both in the edge lengths and in the actual combinatorial structure of the lattice. And so another strategy that people have been suggesting and pursuing is to define the discrete counterpart of the gravitational path integral by taking, again, the exponential of the Regge action, some measure, but then fix the edge lengths to be equal and summing over all possible combinatorial structures, so all possible lattices for a given topology. And again, is in some refinement limit that this gives the full continuum theory. Now, these approaches to quantum gravity are in fact coming from a very conservative perspective. You want to make sense of the quantum gravity path integral and the continuum gravitational path integral, and you go on a lattice to make mathematical sense of it in the first place, and then you try to define the continuum limit. It all makes very good sense. What we try to do, and that's the starting point in a way of for understanding the basic idea of group field theory, is that you take a little bit, in a sense, more seriously those building blocks of your lattice. If you have just a spatial hypersurface, it will be just three-dimensional building blocks. And you take them more seriously in the sense that you don't see them just as a discretization, but as candidate fundamental sort of atomic constituents of space at the quantum level, sort of the fundamental degrees of freedom out of which you have to reconstruct all the rest. So it's the same type of discretization to start with, but then you really focus on these building blocks as if they were independent entities and fundamental entities, not just an approximation scheme. And then you try to imagine what the theory of such fundamental building blocks taken as fundamental will look like. So a given lattice will just correspond to a specific configuration of a certain number of atomic constituents of quantum space. Just like, of course, when you have an atomic system or a quantum many-body system, those atoms can have all sorts of configurations. Well, some of those configurations, in this case, will look like a connected, well-defined, nice lattice. So the first intuitive idea is that you try to define the fundamental quantum theory for such building blocks, for these atoms of space, so to speak, in a quantum field theory language. You want a quantum field theory such that the quanta of the field are these atoms, these fundamental simplices, and then the data associated to each atom, the counterpart to what in usual field theory would be the momenta or the position associated to the quanta of your field, will be instead the geometric data of a single simplex. In the picture here, where the lattice is made out of tetrahedra, then a single quantum would be a tetrahedron. So ideally, this is going to be a quantum field theory of space-time, of the very constituents of space and space-time, out of which you reconstruct space and space-time, and not a quantum field theory like we are used to on some space-time manifold on a given geometric background. So first piece of intuition. Well, you can try to do the same, of course, for space-time manifolds, and that's in a sense where we started from. So even the space-time itself could be chopped in building blocks that of course will be one dimension higher than the building blocks that give you the atoms of space. Now, the lattice in one dimension higher will then correspond in this intuitive picture of atomic constituents to elementary dynamical processes for them. So what are the elementary dynamical processes of a field theory or of a quantum many-body system? Well, dynamical processes in which a certain finite number of the atoms interact by scattering and creation annihilation processes and so on. These are just the Feynman diagrams of the quantum field theory formulation of the dynamics of the same atomic constituents. So the second piece of intuition is that if you really try to construct a quantum field theory of the atomic constituents of quantum space, well, the elementary Feynman diagrams will correspond to such higher dimensional triangulations, so one dimension higher than the atoms themselves. The data that you associate to such elementary dynamical processes will then be the geometric data of the four-dimensional lattice in this 3+1 picture. Again, it's a quantum field theory of space-time and geometry, not on space-time and geometry. So I summarized the intuitive idea. You have a field theory. You want to define a field theory such that the field quanta are such elementary simplices, which may or may not be connected in all sorts of configurations to correspond to lattices as we normally understand them, with connectivity between simplices. And they will be assigned geometric data that encode the discrete geometry of the building blocks of the atoms. Now, this, as I will explain a little bit more in a second, this geometric data can be expressed in a group theoretic language, and that's where the group in group field theory comes from. The domain of the group field theory field will be a space of group theoretic data which have a simplicial geometric interpretation, so a discrete geometric interpretation. So you have a single simplex, that would be a single quantum of your field. It will be labeled by group theoretic data, and I will say more about that. And that means group elements, for example, or representations of a group equivalently. And then your field would be a function of the group theoretic data, for example, the group elements labeling your fundamental atom, your fundamental simplex. What about the processes? Well, the processes, as I said, should correspond to the Feynman diagrams of your field theory. And again, they are also the geometry of the extended four-dimensional lattice corresponding to each Feynman diagram will be encoded in group theoretic data. Your Feynman amplitudes, therefore, the elementary amplitudes for such processes, dynamical processes, will have to be sums over group theoretic data with some weight. The action for your group field theory model, for your field theory of such quanta, of such discrete building blocks of space, will be basically a prescription for such weights, for the weights, and therefore for the amplitudes to be associated to the elementary processes. All of this could be more or less appealing, and I hope is at least reasonably clear at the intuitive level, but the first question should be, okay, where should I then look for the appearance of a continuum space-time in such a field theory? I understand the quanta, I understand the Feynman diagrams. Where does continuum geometry come from, and where does the GR dynamics that such continuum geometry should fulfill come from? So the first point is that when we talk about continuum geometry, and GR dynamics is a field theoretic dynamics, so it requires an infinite number of degrees of freedom. It's a field theory itself, so it cannot correspond to any specific elementary process, any specific Feynman diagram of the fundamental GFT. And it cannot also correspond to the dynamics of any state made out of a finite number of atomic constituents of tetrahedra. You need, again, an infinite number of degrees of freedom. So from the perspective of a hypothetical quantum field theory of such atoms, continuum geometry should correspond to a coarse-grained description of very many such discrete building blocks, potentially infinite, and the GR dynamics should correspond to an approximate description of the collective quantum dynamics of very many such atoms. And I say approximate because the perspective here is that the discrete structures are the fundamental ones, and the field theoretic continuum geometric dynamics is an approximation of that. And of course, this is in the same sense in which in a quantum many-body system, you would normally think of the fluid dynamics or the coarse-grained dynamics to be an approximation of the atomic one. This prompts, as we will see in the later part of the talk, once you have a group field theory model that for whatever reason you like or trust or you find interesting as a candidate description of the fundamental dynamics, well, what you have to do to extract GR or make connection with gravitational physics is to study the renormalization group flow, try to understand more about the continuum phase diagram of the given model, and then extract some collective dynamics. Okay, so that was the very intuitive, the basic intuitive idea. I hope it was bearable so far. Now I'll make it a little bit more fleshed out, trying to stay at the bearable level. So let's look just a single atom of space. So we said that this is supposed to be a single tetrahedron in our 3+1 picture. So I spare you, of course, the details because they're not relevant here, but you can write down in flat Euclidean geometry all the geometric data, the geometric properties of a single tetrahedron. I know you can write down the formula for the edge lengths, for the areas, the volumes, the angles, and so on. What is less obvious, and here you should just take my words, is that you can rewrite the same geometric data in terms of variables which are not just vectors in R3 in flat space, but they are elements from the algebra of SU2 or the conjugate variables describing extrinsic curvature, so the embedding of this tetrahedron in a four-dimensional manifold. They would be SU2 group elements. This can be done in a rather straightforward manner at the classical level. Then you quantize such system. The result is that you get a Hilbert space for a single quantum tetrahedron. And when you quantize SU2 algebra or group theoretic data, well, a complete basis is in terms of what you know from the theory of angular momentum. So you can quantize the angular momentum of a spinning top, and a basis of states for a complete basis of states for such system is given by representations of SU2, that is spins. So that's also what happens in this case. A complete basis for a single tetrahedron is specified by 4 Hilbert spaces, one for each face of the tetrahedron, each corresponding to a spin. So some half-integer representation of SU2. Then there is an additional ingredient which comes from the fact that these 4 faces have to close, and that gives you an invariant tensor in the representation space, in the 4 representation spaces. So the only thing you have to retain from this is actually 2 points. One is that you have a complete characterization of the Hilbert space encoding the geometry of a single tetrahedron in terms of a direct sum of representation spaces for SU2, so collections of spins. And then that you also can quantize and act and make them act on such Hilbert space of states, whatever geometric quantity is needed to describe the geometry of a tetrahedron, the area of a surface, the volume of the whole tetrahedron, angles, and so on. They become operators that act on such Hilbert space, and if you're good enough, you can compute the spectrum of all these operators. So that's the only message. The next message is that just like in the theory of a point particle of any quantum mechanical system, in fact, you can change basis, or more technically speaking, you can change the representation for your algebra of observables. Then you can have, you can go from a position basis to a momentum basis. That doesn't change the physics, it just changes the way you represent your system. The same is true for a single tetrahedron. Just like you can use what is called the spin representation, which is the one I just mentioned in terms of irreducible representations of SU2, so spin values. You can also use group elements as sort of conjugate variables, and there are other bases as well that you can use with some associated geometric meaning. The transformation from a spin to a group basis is called the Peter-Weyl decomposition. Again, take it just as a Fourier transform, generalized Fourier transform, not for functions on flat space, like the usual Fourier transform, but for functions on SU2, or more generally, a compact Lie group manifold. It's the same story. It's a way to map from one representation to the other, from one basis to another. Now, it means that everything I construct out of this Hilbert space, so out of this type of states, for my discrete geometry, and later in my field theory based on such quanta, can always be equivalently written in terms of spins, or in terms of group elements, or in whatever other basis I decide to use. The fact itself is trivial for you, I imagine. The only thing that is less trivial is that, here is applied to in a group theoretic setting, while you're probably mostly accustomed to the standard Fourier transform on flat space. That is the same idea. So I don't discuss it for simplicity, but there are in fact other geometric characterizations of the discrete geometry of a tetrahedron you can use, which instead of using SU2 data, they use the full Lorentz group, and this leads to models of group field theory that are expressed in terms of the representation theory and in general the group theory of the Lorentz group. Now, as you would do for for particles and usual fields, well, you can promote, in a sense, the single quantum wave function to a field, and again, the field will be a function of the same type of group theoretic data that were associated to a single quantum, a single tetrahedron in this case. By the way, maybe I didn't emphasize it enough already, but if anything is unclear in what I say, in the sense that you start having, being a little bit confused about either what I said or where I'm going, then please ask. If you have super smart, interesting comments to make, well, those can be postponed a little bit, and I'll try to answer any question or to cope with your smartest observations towards the end. Okay, so at this point, I only described the quantum theory of a single building block of space, a single atom of space, the quantum tetrahedron, and then the idea is that I go towards a field theory description. So the first thing that you would be interested to do, even before going to a full field theoretic description, would be to ask what happens when you glue together quantum tetrahedra to form extended structures. Well, without going into details again, I just want to mention the key idea. If you have two tetrahedra, you have a tensor product of the Hilbert space I just introduced for a single tetrahedron. For each of the two factors in the tensor product, you can choose a basis that is the one in terms of spins. Now, it's a fact that is quite remarkable in a way that the very moment you impose that instead of considering a product state in such a basis, you want to consider a maximally entangled state. So you want to force the two spins to be equal and then trace over the intermediate vector indices, like you will construct a maximum entangled state for two spin 1/2 particles, generalized, of course, in this case to generic spin. Well, a state so constructed as a geometric interpretation, if you look at what happens to the various geometric operators, as corresponding to two tetrahedra that have been glued that share a triangle. So they agree on its area, they agree on what the parallel transport from one tetrahedron to the other does, and so on, so on. So what is interesting here is that at this quantum discrete level, entanglement is directly related to the connectivity of your discrete structures. In fact, the interest goes beyond this. Even if you start asking questions about, on the one hand, geometric operators, areas, volumes, and so on. And on the other hand, you ask questions about entanglement measures for such entangled states, well, you find a correspondence. You find, for example, that the local measure of entanglement associated to the shared triangle is in fact proportional to the area of that surface. If you ask about the entanglement that is associated to the four faces bounding a given tetrahedron, well, a measure of that entanglement is proportional to the volume of the tetrahedron itself. Okay, so somehow it seems that there are also some quantum information seeds of the emergent geometry that you can try to reconstruct out of putting together such building blocks, some atoms of space. Anyway, I told you about the Hilbert space of a single atom. I told you how to construct Hilbert spaces for several of them and how to glue them. Well, what you can do to include all possible such states is to simply write down the Fock space out of the individual one-body Hilbert space. You have to assume some statistics. Let's consider bosonic one for simplicity here. And then any Hilbert space associated to tetrahedra glued together will be, in fact, a subset. In fact, a sub-Hilbert space of such Fock space can be embedded faithfully with the right inner product. Once you have a Fock space, then you can introduce creation annihilation operators that help you move around the Fock space. You literally create, annihilate tetrahedra endowed with a given set of geometric data. These are going to be, of course, the group field theory field operators. Because I assume the bosonic statistics, these are the commutation relations that you expect. And whatever geometric operator you add in the original formulation, just in terms of Hilbert spaces for individual tetrahedra, as a second quantized counterpart obtained in the usual way by convoluting matrix elements of the sort of first quantized geometric operators with field operators. And I wrote here the example of the volume operator. You can consider the volume of a single tetrahedron. You convolute it with the field operators using either the spin basis or the group basis, whatever basis you want. The result is invariant under that choice of basis because it's a full convolution. Then this has the interpretation of the total volume you associate to a bunch of tetrahedra. Just like, because it's an extensive quantity. So just like, I don't know, the total momentum of a bunch of atoms is constructed in the same way by convoluting the momentum operator of a single atom. And the result is the sum of momenta contributed by all the atoms in your quantum state, if you apply to a given quantum state. Okay. It's worth emphasizing that if you just take a generic state in this Hilbert space, on the one hand, it has no specific reason to be an entangled one. I mean, yes, generic states will be somehow entangled, but they will not correspond to the maximally entangled ones that I've shown in the previous slide. And I mentioned that the trivially connected tetrahedra. Moreover, this will remain highly quantum. Whatever geometric assignment you try to give to the tetrahedra in such a state, well, it will not give you a classical discrete geometry. It will be subject to uncertainty. You will be able to specify only some of the geometric data and not others, and so on. It's a quantum system. At this stage, it should be already quite intuitive for those of you who know about loop quantum gravity, what the connection is between group field theory built in this way and understood in this way and canonical loop quantum gravity. Well, the simple points are that a quantum tetrahedron can be understood as a single spin network vertex, and the entangled many-body states in the GFT, made out of many glued tetrahedra, just corresponds to the spin networks that are the basis of quantum states in loop quantum gravity. And as I said, those states are just naturally embedded in the Fock space of the group field theory. The full Hilbert space, however, is different. There's no Fock space in loop quantum gravity for the spin networks, so clearly there are a number of differences. In fact, you can extend the correspondence at the dynamical level, although in the sense that for any assignment of group field theory dynamics with this type of data, you could extract a prescription for a loop quantum gravity Hamiltonian operator, more properly a projection operator, and in principle vice versa. But as far as I know, nobody's really tried to use this correspondence to build up models in GFT coming from the canonical theory or vice versa. Anyway, it's from this point of view that one could say that the group field theory can be understood as a second quantized version of loop quantum gravity because of the Fock language. Now, I only spoke about states so far, but that's not so interesting. What you really care is the dynamics. What you care about is the dynamics. So let's see how one should understand the dynamics in group field theory. But again, I will start from some simple cases first. So let's just consider a point particle. And in fact, I separated the fact that it's a point and a particle because the point-like nature of the object reflects on the combinatorics of the elementary processes, which are the Feynman diagrams. And then I don't care if you want to label your particle by position or momentum. I just call I the type of data associated to the particle. This somehow encoding its physics. So the combinatorics is, well, straightforward. You have lines of propagation, and points of interaction where different lines of propagations meet. And this combinatorial structure follows directly from two ingredients. One is that you are dealing indeed with point particles, and the other is that you require local interactions. Also, interactions happen at a point. And then you have physical data, as I said, momenta or positions, and what the theory should give you, if you want to compute probability amplitudes for such elementary processes, as you know very well from standard Feynmanology, are interaction kernels and propagators. And these are the ones for a scalar field theory, which you can also read out or encode if you go back in the action for a scalar field theory, where the kinetic kernel is the inverse of the propagator. And everything can be written, I will keep stressing it a few times, either in position or in momentum basis. Is all clear so far? You still with me?
In principle, yes. Are there any questions? It seems that's not the case. Please go on, Daniele.
Okay, good. So I take this to mean that, so far you are following. So that's encouraging. Now, let's start generalizing a little bit. And instead of point particles, we consider matrices, which are in fact understood graphically, not as points, but as links. A matrix has two indices, and I don't want to, it's not important what these indices refer to. Let's just take them to be in some finite set. And then the combinatorics of the diagrams can be represented in a number of ways. It can simply be that the line that is the matrix moves in some embedding space if you want to embed things without changing combinatorial structure, or you simply follow the two indices that carry the physical information, and this identify two lines of propagation. So that's not the interesting part. The more interesting part is what you may want to do with the interactions. At the interactions, you have, of course, choices, but things become interesting the moment the indices of the matrices that interact, let's say there are just three of them, do not simply identify indices, but they identify them pairwise. So one index with one matrix is identified with the index of another matrix. The second index of this second matrix is identified with the index of a third matrix, and the remaining two indices of the remaining two matrices are identified. This type of combinatorics, if you draw it in terms of lines that share points, the endpoints of the lines corresponding to the matrices, will draw for you a triangle. Whatever is the combinatorial interpretation, this simple gluing can be implemented in the simplest form in terms of identification of the finite dimensional indices through Kronecker deltas. And then, if these are your building blocks of your Feynman amplitude, well, they can also be encoded in a matrix model action, where your matrix is a sort of, in quotes, a field of links. The links are your basic entities, discrete structures that you propagate, you create, annihilate, you make interact in the elementary processes. Everything is governed by the dynamics encoded in this action. Well, if this is still fine for you, then I can move on after showing you an example of a Feynman diagram of a matrix model, of the order 3 matrix model I've illustrated in the previous slide. Well, then I can move on to the higher rank and higher dimensional combinatorial structures. Let's consider a 3 tensor, a tensor of rank 3, this can be understood graphically as a triangle with 3 indices associated to the edges of the triangle. Then the combinatorics could be more interesting, much more interesting, because on top of just, the propagator just propagates, okay? But the interaction combines 4 such triangles, forcing them to have edges identified. And if you take 4 triangles and identify edges pairwise, as I did for the matrix, you get again a simplicial structure, so a tetrahedron. Be careful, here the tetrahedron is a building block of the process, not of the states. The states are given by a bunch of quanta, which are triangles. But once more, you can write down a propagator and an interacting interaction kernel, and you can then write down an action that encodes exactly the same information.
Daniele?
Yep.
There was a question in the Google form. So the question is, what do you mean by interaction in GFT?
Well, in this context, I just mean what I said, which is that there will be a process in which the quanta can be created and annihilated with the elementary creation annihilation process as the combinatorial structure that I give in this example. Nothing else. I mean, the interaction is not yet physical in the sense of, I don't know, things moving on a space-time and doing things or carrying energy or exchanging momentum.
Thank you. I think that should be fine.
Does that help?
I would think so, yeah. Thank you.
You're welcome. So I'm really trying to take it first at the more formal level, but trying to clarify the combinatorial aspects, because they are the ones that at the formal level really mark the difference between usual field theory and group field theories. If those are under control, the rest is the physics, and I will talk about the physics in the second part.
This is perhaps a good moment, Daniele, I'm sorry to interrupt, just to remind you that we would appreciate if you would finish in around 15 minutes.
Mm-hmm.
Is that possible?
Yeah, I can always 15 minutes. I will go a little bit faster then, and then in case I'll stay longer for questions. So the 4-dimensional and possibly higher dimensional story is exactly along the same lines. You're going to have a field that corresponds to 3-dimensional simplices and 4-dimensional dynamical processes, and an action that governs those processes. At this stage, I don't want to discuss any specific model, so there will be some action, and the peculiarity is that the interaction term in the action will have to have a pairing of arguments which reflects this combinatorial structure of gluing together in a non-trivial manner the simplicial building blocks. And you can expand a partition function. You can write down a partition function for that you can postulate it, but then what you actually try to define is a sum over Feynman diagrams built out of that in perturbative expansion. And the Feynman amplitudes will correspond to the usual convolution of propagation kernels with interaction kernels taken from the action, and they will involve a sum over the group theoretic data that I mentioned. I mean, if you have a quantum tetrahedron in a more geometrically interesting model, you will have to integrate over group elements or sum over irreducible representations of the group. You can think of these amplitudes as a discretized gravity path integral, and this is justified in 2 ways. Well, the amplitudes of a group field theory, if it has all this type of geometric data encoded, included in the model, can be shown to be equivalent to a spin-form amplitude, in the sense that for any choice of action in the GFT, you can define amplitudes in your spin-form models, if you know what those are. And the point is that those are themselves a sort of algebraic realization of the idea of a discrete path integral for gravity. And in fact, they come out as the evolution of spin networks in canonical loop quantum gravity. But then by changing variables, and I'm not going to do it, of course, you can show that the same amplitudes written in different variables can take the explicit form of lattice gravity path integrals. So literally coming from taking the continuum action, discretizing it on a lattice, writing down the path integral with some choice of measure on the lattice. Then for every lattice, there will be a corresponding Feynman diagram of a group field theory, for which the Feynman amplitude is the path integral you wrote down. Concrete models to give a little bit more flesh to the general structures. One is the one I already mentioned for a tensor model. Everything is purely combinatorial, and the amplitude is what I wrote on the slide. It's just a function of the parameters entering the model, the coupling constants and the size of the tensor, n, and the combinatorial data, number of phases, number of loops, number of vertices in your Feynman diagram. So number of loops, number of links, and number of vertices in your Feynman diagram. A more interesting model is the one in which you quantize not tetrahedra in 4 dimensions, but triangles in 3 dimensions. And without going through the whole thing, you can write down the model. The basic field is a function of group elements taken again from SU2. And the Feynman amplitude, which you can write down explicitly in different variables, well, are recognized to be a lattice gauge theory formulation of 3D gravity in one set of variables, the group elements, or the spin form formulation of the same 3-dimensional gravity theory in the representation variables. And in fact, if you write it in further change of basis, then you recognize directly the discrete gravity path integral for the discrete version of the Palatini action in 3 dimensions for gravity. This is a Riemannian model. Okay, and then just to scare you so you don't ask more details, in 4 dimensions, you can also write down a bunch of models. They are much more involved from the algebraic point of view. And there's absolutely no need here to go into any such detail, let alone those of the amplitudes. The point is simply that they're constructed using exactly the same principles. You quantize the tetrahedron in a given set of variables that are group theoretic, so group elements or representations of a group. It can be SU2 or Lorentz. You have to make sure you encode geometric constraints to have a good interpretation for the data you have. And then you put them together to define an interaction vertex for the field theory and a kinetic term for the field theory. The rest will follow along the lines of what I tried to explain. Now, no, I'll skip.
Daniele, maybe before you move on, there was another question before. So
Sure.
could you view the spin-form quantization as an example of GFT quantization?
Now, GFT quantization is the construction of a GFT model out of the geometric quantization, for example, or any other quantization method applied to a single tetrahedron along the lines of what I said. So the only quantization step in a literal sense of the word, you have a classical system, then you quantize, is the one I mentioned at the very beginning. You can write down the geometry of a classical tetrahedron in Euclidean space as in terms of a phase space and functions on phase space that encode the geometry, all the possible observables of a single tetrahedron. And then that thing you can quantize. Which method you use doesn't really matter. The result is the same. You can choose geometric quantization, for example. That's the most common one, but you can choose other ones. Once you have that, there's no more quantization to be done, and you follow these construction steps that I said to define the Fock space, to define an action for the groove field theory that will produce the Feynman diagram and Feynman amplitudes you're interested in for other reasons, or you can proceed from classical gravity, as I mentioned, discretizing on a lattice, and then looking for the groove field theory model that will produce that discrete path integral as an amplitude, as a Feynman amplitude. But there's no quantization of GFT as such, because we don't know, I mean, there may be, but we don't know what would be, say, a canonical formulation of a groove field theory, bar a number of caveats that I'm happy to discuss. Does that help?
Yes, I think that helps. Actually, also there is another one in the chat. So can GFT quantization be used to quantize string theory, for example, by considering the representation theory of
I'm happy to discuss
algebras?
it. Yeah, I'm happy to discuss it, but later.
All right. Thank
So
you.
at the end of the talk, so for now, let's stick to the, in my last, I don't know, 5 minutes or 10 minutes, to the only two things that are needed for understanding what I'm saying, so that we have a basis of intuition, and then I'm happy to tell you what we know and what we don't about GFT.
Sounds good. Thank you.
For 2 hours if needed. Okay, so anyway, so we have these examples, and I skip all this about the nomenclature, is not important, because in the literature you find a number of names applied to the formalism. I emphasize some connections to other approaches, and I think this is an appealing feature of the groove field theory formalism. Anyway, so suppose that you have a groove field theory because you come from spin foam, because you come from lattice path integrals, or simply because you have some geometric structure like a classical tetrahedron, maybe endowed with additional degrees of freedom that you quantized and you want to promote to a fundamental building block of your field theory, and that will be a groove field theory. What do you do with it? Well, there are two things that I want to mention at the end, which have to do not anymore with the basic ingredients of the formalism as such, but indeed with applications and trying to go in the direction of physics out of it, in particular quantum gravity. So the first thing that I will say is that if you start from a groove field theory, some action, a partition function, a sum over Feynman diagrams, well, the first thing is that if you really want to trust the intuition and your construction principles that come from these Feynman amplitudes and from the perturbative expansion, from lattice path integrals, all of the things that you can see in this perturbative expansion, well, you have to make sure that the ambiguities that enter any lattice path integral, any spin foam amplitude, and in fact beyond, are under control. This, in fact, is another way to say that you want your quantum field theory, initially defined perturbatively, to be under control for all ranges of the dynamical variables. And this is another way to phrase the issue of perturbative renormalizability of a field theory. So one thing that a lot of people have been devoting their time to is to show that groove field theory models of various types are perturbatively renormalizable. So they are actually well-defined quantum field theories, even before you try to apply them to particular physical situations. So that's one line of research. The second one is it's more important in a way for extracting gravitational physics, which is our goal, of course, in quantum gravity. And it's the following. So the moment you have quantum gravity degrees of freedom, or in general, degrees of freedom interacting with each other, and this is the case when you have a quantum many-body system, well, you keep in mind that the physics of a few degrees of freedom is very different from the physics of many degrees of freedom. This is an absolute triviality, and you want to control what happens when you increase the number of degrees of freedom. From a lattice point of view, or a canonical quantum gravity point of view, or a spin form point of view, it means that you want to know what happens when you refine, when you consider many tetrahedra, or refine your spin form amplitudes, or refine your lattice path integral, and you go towards a continuum limit. What you should expect to happen is that you find different continuum phases and phase transitions. So which one of those has an interesting continuum geometric meaning? Which one of them allows you to extract general relativity, at least approximately? This is a typical problem in any quantum gravity approach, especially, of course, these discrete ones, and it translates in the group field theory setting into the problem of controlling the non-perturbative renormalization group flow of the given group field theory model you are considering. And as I said, is a translation of the same problem that you have in lattice quantum gravity, in spin form models, and in loop quantum gravity, and you name it. Okay, so from the formal point of view, renormalization group analysis of group field theories doesn't present initial challenges, in the sense that if you don't think about the physical meaning of the geometric meaning of your manipulations, well, you have a field theory on a group manifold. The group manifold has some topological structure. In fact, it has a metric. So you can define scales as usual, and depending on that metric, and they will basically correspond, they will basically be indexed by the representations of your group. Just like in usual flat space field theory, the scale is indexed by the momenta. The challenge comes when you, from the fact that you have to consider the combinatorics of the Feynman diagrams, of the interactions, and so on. That's where you need a lot of work to adapt usual techniques to this case. Without dwelling more into the details of that, I'm happy to discuss, but people have done a lot of work in this direction. And I just want to mention that the geometric perspective on what you do will have to be, you have to be very careful about it, because what counts as UV or IR from the formal point of view in GFT may not correspond at all to anything that you will call UV or IR in the in continuum geometry, because those are defined in terms of a metric. And there's no background metric here that you can use. Okay, I can tell you how you could interpret the various regimes in GFT based on what we know from discrete gravity. But for now, I just urge caution. Anyway, I skip all the results in perturbative and non-perturbative renormalization.
I would appreciate it, Daniele. I'm sorry to interrupt. If you could conclude in the next couple of minutes.
Yeah, so I'll just mention briefly the cosmology story, and then I'll quit. I'll stop. Okay, so I'm happy to answer questions about results in renormalization theory. So what about cosmology? Well, the first point that should be clear is that in GFT, space-time and geometry are necessarily emergent, because you start from fundamental degrees of freedom and generic states that do not admit even a nice discrete geometric interpretation when taken together, because they are quantum, because they may be disconnected, and so on. So space-time is emergent, and the extraction of some effective continuum dynamics out of a quantum many-body system is the typical problem in quantum many-body physics and condensed matter. And GFT gives you some language in common with that domain. So cosmology is expected to be the sort of most coarse-grained dynamics. And so we are interested in looking for a hydrodynamic type approximation of the group field theory dynamics. So I'll skip what we can expect and I tell you what we do. So the general strategy is to look at the universe as a sort of a fluid made out of these quantum gravity atoms, specifically like a condensate. If you have such a quantum many-body system, then you can extract some approximate hydrodynamic equation for the fluid. Once you have such hydrodynamic equation, you need to turn the equation for the dynamical variables of the fluid, which will be some density and some phase, into equations for observables for which you have a cosmological interpretation. So starting from some group field theory model, any group field theory model, then the simplest hydrodynamic approximation basically corresponds to the classical equations of motion, is the mean field hydrodynamics. It corresponds to work with a very simple type of quantum states, and this is the approximation which we have been working mostly so far to extract cosmology. Then you need to extract things in terms of observables in order to compare with continuum physics. And the observable you need to use are relational or diffeomorphism invariant observables, simply because there's no manifold, there's no coordinates, there are no diffeos in the sense of space-time diffeos in the fundamental theory. In order to do that, you need to introduce matter coupling. So not only you need matter because, well, it's a content of the universe, but also because you may use it to define some physical frame to define relational observables. And I skip how you do that. Okay, two facts are true in general, which is that the domain of a condensate wave function, so the mean field that is the dynamical variable of hydrodynamics in this approximation is the same, is isomorphic in fact to the mini superspace of cosmology, the space of homogeneous geometries. And the classical equations of motion will look like a nonlinear equation for a function which is your mean field on such mini superspace. This means that it's a nonlinear extension of quantum cosmology. Then you can compute observables in your states and turn the equations for the wave function, so these nonlinear equations, into equations for cosmological observables, for example, the total volume. Okay, and then in some interesting models, there are a number of results that we have found that I'm happy to tell you more about. Let's just say that, first of all, we checked that there is a decent semi-classical limit at large volumes under the dynamics governed by the hydrodynamic equations of the condensate. At early times, instead of a singularity, we found a bounce. And in fact, under some additional conditions and assumptions, of course, at late times, we find something like an accelerated expansion of dark energy type. So this doesn't mean, of course, that the models, the specific models for which we obtain these results are right for physics, but at least they are encouraging that they're not totally wrong. Okay, and I skip all the other results and I just say the obvious, which is that there are clearly many more things to do, and I'm happy if you want to join. And I thank you for your attention.
Thank you very much, Daniele.